active geology is a major pain for trying to study the early Earth.
You're listening to The Cosmic Cast.
Hello, and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. Your usual hosts today, it's me, Marissa Lowe, joined by John Pernay-Fisher.
Hello.
Ricky Bahir.
Hello.
Tom Harvey.
Hello.
And our special guest this week is Dr. Sam Royle from Imperial College London. Hello,
Hi.
Sam. How are you doing?
Hi.
Nice to meet you. How's it all going?
It's going well, thanks.
Good. So you research Mars, and more specifically, you look at organic material on Mars. So yeah, would you mind giving us a rundown of what your main research areas are?
Well, honestly, at the moment, I'm not employed to look at Mars. I'm actually looking at surface processes on comets.
Ah, cool.
But I'm going to talk with you about Mars today because I know a lot more about that. But yes, been looking at the interactions between organic matter and minerals on the Martian surface, specifically when they're trying to analyze them with the rovers, because the techniques that they use with the rovers involve heating up the soil samples to release the organic matter that's in there. And it turns out that with various minerals present, we have various issues when they're heated as well. Some minerals have catalytic effects, increasing the breakdown rate. Some minerals have transformative effects and turn the organic matter in there into completely different things. And other minerals just release a shed load of oxygen and basically blow up the organic matter present. And that's the main issue that they've been seeing on Mars so far.
So when we say organic matter, what sort of things are we talking about? Are we talking sort of amino acids or like other sort of complex molecules?
Well, we'd love to find amino acids on Mars. There's amino acids in meteorites and various things like that, fatty acids. But so far, all they've detected on Mars really is a sort of kerogenous type material, like complex macromolecular stuff made out of aromatic rings, because that's what we're talking about. Organic matter that's been on Mars for about 4 billion years and then been buried and then re-exposed at the surface for us to be able to get to. Because anything on the surface where you might potentially find amino acids and things like that will just be wiped out by cosmic and UV radiation.
Yeah, that's really cool though. That's amazing that they can be preserved over such sort of long timescales.
Yeah, we think they should be able to. Yeah, so there's a lot less going on at Mars to destroy these things as long as they're protected from radiation, because you don't have the bacteria that we have on Earth breaking things down. You don't have the plate tectonic processes that have destroyed anything of that age on Earth through metamorphism and things like that.
Yeah.
So is there a reason that they don't use, so unfortunately I don't know very much about the tools that are used to identify organic matter, but is there a reason they use tools that heat up the material prior to actually understanding what's inside it? Is there no way of doing it without having to heat it up?
Yes, so I mean, solvent extraction, which is the other way of looking at organic matter in samples, is a bit more complicated to do. It's better with like a rover instrument. It involves taking a lot of chemicals, which are all organics themselves up there. So it's introducing a lot more variables, a lot more things to go wrong, and the amount of more moving parts that the rover would have to do would be quite a lot. But the main thing is the types of organic matter that we would expect to find on Mars surviving after 4 billion years are not going to be solvent extractable. They are going to be these large macromolecular molecules that you're going to have to need to heat up, really. At least so far, ExoMars is going to have a laser, which will do the same sort of job, but hopefully without the mass heating. It'll be a much more sort of focusable, direct way that hopefully won't have as many issues. And it will also have derivatization techniques, which combines some sort of chemical technique with lower temperature heating to break things down without having to heat as much. which should be pretty handy.
Hmm.
And
Um,
ExoMars is actually planning to drill below the surface as well. So would you expect that below the surface you might have all these organics you're not seeing on the surface?
Yes, hopefully, because any rocks that we've been able to get to so far have been exposed in the near surface for millions of years. So they are going to have been subjected to radiation, and that really is just going to annihilate anything in the near surface.
So do we have any idea of where these organic molecules came from in the first place? Were they produced on the surface of Mars, or were they more delivered there?
Yeah, I mean, Mars should have had just as much organic matter in the first place as Earth, because coming from meteorites, comets, and over the last, since the atmosphere failed there around about 3.5 billion years ago, it will have had much more organic matter reach the surface through micrometeorites and interplanetary dust particles, which will just burn up in the Earth's atmosphere. So there should be plenty of extraterrestrial, well, extra Martian organic material at the surface of Mars. But also, as we now know that back in the past, Mars was quite geologically active with volcanoes and hydrothermal systems, there's plenty of scope for organic materials to have been produced in that way at Mars. So we should be looking for both indigenous and endogenous Martian material.
And would you be able to decipher between the two?
That is the hope. Anything that's about 4 billion years old might start getting a little tricky. But if we can get around all of the secondary processes that are happening during analysis, it is hoped that that would be possible.
And how, I guess it's probably a very complicated process, but how does one determine the difference between them?
Oh, that's a very good question. That is kind of the question.
Presumably these sorts of things are at quite a low concentration in the soils to start off with, so they sound like quite challenging measurements.
Yes, they are, especially in the near surface environment where we will have lost a lot of it. And also because anything that will have organic matter in it has probably been buried to depth and then re-exposed. Especially that's what we've seen in Gale Crater. We know the sediments have gone down to roughly a kilometer's depth and then come back up again. All these processes will have altered and damaged any organic material there.
How do you go about recreating some of these processes so that you can analyze them in, presumably in a lab? Is that?
Well, when we're just looking at what's going on inside the rover instrument itself, that's quite easy. We just use, they use thermal desorption techniques coupled to the mass spectrometer. We use pyrolysis techniques. Both techniques are just ways of heating samples to volatilize any organics in there. When we're looking at what's going on during the burial processes, we use a technique called hydrous pyrolysis. And basically we take a small sample, put it in a reaction vessel, which heats up to about somewhere between 200 and 300 degrees. That create with water in it. That creates steam to create a high pressure environment. And we basically use higher pressures and higher temperatures to replicate what would take a really long time to happen on Mars in burial, but just over a weekend.
So I guess this is the ultimate question. Why are organics important? Why do we need to understand the organics of Mars? What can they tell us? Well,
we don't know very much at all about prebiotic chemistry on Earth. It has been lost by, the last 4 billion years of having life and metamorphism and
Geology,
plate tectonic cycling. Yeah, just geology. Active geology is a major pain for trying to study the early Earth. And you just don't have that 4 billion years of destruction on Mars. So anything we learn from Mars's prebiotic chemistry, which probably never got to the biotic stage, may be able to teach us about how we got from prebiotic chemistry to biology on Earth.
Mm.
It's still, astrobiology is really, in a lot of cases, the study of the origin of life on Earth by looking at other places.
Yeah, yeah. So by understanding the sorts of compounds that are there, do we get a sense of the sort of physical environments as well that these sort of molecules may have formed in, or is it literally just this is a thing that is here?
We should be able to figure out the sort of formation environments, yes. I mean, when we did our work on the Tissant meteorite, which is a Martian meteorite that landed in Morocco in 2011, so we've looked at the organic compounds within that, and by looking at both the organic phases and the inorganic phases, we can create a picture of what was going on in that little bit of the Martian crust before that meteorite was ejected. And we can work out the composition of the fluid flows that were going through the crust. We're pretty sure that they were in quite a near surface environment to have reacted with the Martian atmosphere at the time, and work out the redox environment, all that kind of things, based on, because you need both the organic and the inorganic phases to do that. They don't tell the story by themselves.
Yeah. So that's quite interesting then. So a Tissant, I guess, is for people in the audience who may not be aware, I guess, is effectively a lump of basalt, isn't it?
Yes.
So are these organic compounds then, are you finding them within like cracks and fractures in the rock? I mean, presumably they're actually not held within the minerals themselves.
Well, the way that we look at bulk analysis when we do it. So basically I received a ground up piece of the meteorite and put it into the pyrolysis instrument. So I couldn't tell you where exactly it's hosted, but other studies, I think, suggest that they sort of stick on the surface as some of the mineral grains.
Yeah. So that must be really difficult then, trying to find fresh enough samples that haven't been affected terrestrially in that respect.
Yes, there is. I mean, most meteorites have been on Earth for thousands, if not millions of years before we find them. Tissant was pretty special because they saw it land, and it landed in a desert environment, so there'd been no rain in the intermediate period.
Yeah. So that's amazing then. So you've been working then with physical samples and rover data then. That must be quite a sort of a unique insight then to sort of combine these different data sets.
I mean, yeah, it's pretty cool. I mean, it's really cool when we see very, very similar kinds of organic matter being detected on Mars as we're detecting in Martian samples.
Yeah.
And it's just a really nice way of corroborating things.
Yeah. So you actually involved with any missions at the moment, or is it you just sort of just seeing what sort of data is out there?
No, I don't have any actual links to the missions, unfortunately. We just see what gets put out by them.
Yeah. So I guess, so presumably then, just thinking then ahead to ExoMars, then are you quite excited about where it's going to be landing and what that could tell you in terms of its organic chemistry? Because presumably previous rover missions haven't really factored that too much into their considerations of where they land.
No, very excited. I mean, ExoMars is a proper life detection mission.
Yeah.
So, and with the suite of instruments it's got, I'm very excited about it. It's going to be able to do things that nobody's been able to do before. It's our best shot at finding any sort of organic matter on Mars and, figuring out what's going on there.
Yeah. I suppose lots of people get excited about the question of is there life on Mars a lot, and even more so with ExoMars and other missions that are coming up. What would be the big headline findings that you would love to see from those kinds of missions that would help answer that question?
Well, what we'd love to see is some proper biomarkers, like organic matter that cannot have organic compounds that cannot have formed in any other way because they're too complicated, and what we want is unambiguous data. So far, we only get ambiguous data. That is what the issue with all the rover data we've had so far. Everything that we found could have been produced in many ways, and all of the arguments about how did it get produced. What we want is the smoking gun. We want, like some steranes or something like that, hopanes, but we're not going to be finding them too close to the surface. Like they're the kind of things that are just going to get broken down by UV.
Yeah. So do you really think then, if we wanted to find this smoking gun, will that require 2 feet on the ground and people actually exploring? Or do you think rovers are even capable of ultimately trying to detect these sorts of smoking guns?
Well, yeah, I mean, a big problem if we're looking for evidence of life on Mars is that even 4 billion years ago, it's quite likely that habitats were transient.
Mm.
They were never habitable for a long period of time. So you're just going to have very discrete pockets, and just the chances of finding a pocket where there was evidence of life
Mm-hmm.
and in an amount that is detectable, it's just so slim, even if you had people on the ground.
Yeah, I guess I mean, we banned about ages like 4 billion years, but I suppose it's hard to sort of comprehend really quite what a huge amount of time that is. And as you say, if you're trying to find sort of transient things that even only last, a couple of million years, say, that's still like tiny compared to how big a billion years are.
Yeah, well, if that as well. So from my work on Martian river systems, the longest lived ones we're thinking on tens of thousands of years that
Really,
fluid
that's a
activity was
drop, isn't it?
occurring for. Yeah.
Yeah,
So it's
yeah,
a drop in the ocean of time,
yeah.
really,
Well,
But I guess it
yeah,
comes down to the question of how long does it take for life to form as well, And I guess these are questions hopefully we might get a step towards the answer from looking on Mars.
Yeah, so you said that Mars was probably actually more useful for studying how life on Earth started than Earth is. What sort of environments or analog things would you look for on Earth to help you understand both Mars and Earth?
I mean, if we're looking at the formation of life on Earth and Mars, probably talking about maybe hydrothermal systems and vein systems, both of which we found on Mars. Um, and I mean, on Earth, these things are full of life. So we've got to, yeah, we really want to be finding these sort of like smoker type environments on Mars, which people think that they might have found evidence of, but we just really need to
yeah,
get in and explore them if they are there.
yeah. So yeah, these are black smokers, aren't they? Aren't they underwater hydrothermal systems, aren't they?
Yeah,
And
on
I guess
Earth.
importantly, they're associated with like volcanism, aren't they? I suppose do you tend to find them along sort of ocean ridges and stuff, I think.
Yeah. And though I mean, we know there's plenty of volcanism on Mars back in the past.
Yeah,
So hopefully we can find one of these things.
yeah.
And if we
Is
do,
the association because these black smokers release nutrients that's beneficial for life formation, or
yeah, in the hydrothermal systems that feed them, you are creating organic matter. So you're creating the ingredients life needs. And there's all sorts of useful metals and things like that, the life wants as well, coming out of these things. So they're super productive environments. So
Yeah,
if life is going to evolve somewhere from weird prebiotic chemistry, it's likely to happen around something like that.
yeah.
That's the theory that I favour anyway.
Yeah. Well, yeah, I was going to ask actually, because I remember learning about black smokers and stuff in undergrad. So is that still the sort of predominant theory of how life started on Earth? Is that what's favoured generally in the community still?
I think it is within the astrobiological community because that's the one that gives us the best shot for other planets. Because even if we go out and look at things like Enceladus,
Well, yes, yeah.
like
All these ocean worlds.
all the ocean worlds, we think that kind of thing's going on there as well. So got to stay hopeful.
Yeah, absolutely.
we aren't finding a nice little warm puddle at the surface there.
So would you consider yourself to be an optimist when it comes to potentially finding life in the solar system?
Yeah, I reckon so. I'm one of those people that thinks we don't have any reasons not to believe that there might be something out there. So why not? There's too much interesting stuff out there to start with. Especially if we start thinking about places like Titan. Like the prebiotic chemistry there is going to be intense when we finally get a mission there. We're not going to have a clue what's going on. There's going to be so many signals.
So you said at the beginning that you're now moving on from Martian work to is it asteroidal work, cometary work?
Cometary surface processes,
Right.
yeah.
So what's taking there?
Funding.
Yeah, as usual. Yeah.
Yes, that's the money my boss got, so that's what I'm working on.
Fair enough.
I do hope to come back to Mars sooner rather than later, though.
Yeah.
Yeah. And I suppose comets are also chock full of organic compounds, aren't they?
Yeah, we're looking at the exact same processes, except rather than working out what's going on inside a rover, we're working out what's going on at the surface with organic matter, and currently trying to look at the mixture of UV radiation and thermal processing, just heat,
Okay.
and compare what if you take some starting molecules that are likely to be there, what would you actually detect after they've been subjected to UV or heat for a few million years? What's left behind? How can we use that?
Yeah, well, that seems really important, though. I mean, I guess it's still related to Mars in a way, isn't it? Because I guess these are sort of things that would have been impacting into Earth or Mars 4 billion years ago, regardless.
Yeah, there's still the source matter.
That's really cool. So you're using Rosetta data and things like that as well, or?
We've not got as far as combining its data. We're still building the instruments. We've
Okay.
been developing a planetary environmental vacuum chamber with a big UV light, and that's going to be pretty cool once we get it up and running. But it's had so many problems with leaks, and 7 months of not being able to get into the lab to tinker with it has been a bit of a pain.
Yeah.
Yeah. Have you been able to adjust the work that you're doing much during lockdown?
It has not been a productive period now.
Well, yeah, join the club.
Yes. Fortunately clashed with me having a big block of lab experiments planned.
Oh. Good question, Marissa.
Yeah. I know, it's always which way is this going to go when we ask people this question?
Yeah.
Yes, no, I'm not one of those people that's been churning out papers during lockdown.
Yeah, it's always upsetting to see, isn't it?
Yeah.
So I guess we didn't even ask, obviously, what you're doing or what you plan also to go back to doing, looking at organics on Mars, is very cool, very interesting work, and obviously has some clear implications for understanding life. But what got you into it in the first place? How did you get to that point?
In the long story, an obsession with dinosaurs as a small child. Goes dinosaurs, geology, then somehow switched into geochemistry with my undergraduate master's project, which was just looking at carbonate concretions in mudstones. That link into carbonates then took me to the University of East Anglia to look at corals, coral geochemistry, and trying to look at the paleoclimate of the Mediterranean. And the techniques that I used in that then somehow got me a job looking at Mars.
That's really cool.
The logical next step after corals, I think.
Is Mars.
Yeah, it's none of it made any sense. And that was, to be honest, that was after my PhD. I spent a year out of academia just applying for anything, anything using GCMSs. Imperial was the place that bit.
Yeah, it's always quite odd, isn't it, how sort of randomly these sort of things work out, I suppose. But yeah,
it really is. There does seem that whether you want it to or not, all roads lead to astrobiology.
I've not actually heard that famous saying before, but
did you miss doing terrestrial stuff at all then? Do you think you would ever be tempted back to corals or anything?
Oh no, they were horrible to work with. Absolutely horrible. My thesis is just a book of null results. There are 2 papers from my PhD, both telling people just do not bother doing this. It doesn't work. It's a lovely idea trying to get these trying to work out these paleoclimate thermometers, but corals are not just passively uptaking things from the sea. They're living things. They do all sorts of weird stuff as they're as they're growing, and one corallite growing a meter away from another corallite is not doing the same thing.
Yeah.
You've got, the water flow, they're taking different amounts of food, so they're taking up different amounts of inorganic things as well. So it doesn't work.
Hey, you managed to get 2 papers out of that, though. So,
Yeah.
yeah. Good job there.
Yeah,
I
that's
guess
quite nice.
somebody had to
You're-
waste 3 years, so somebody else didn't have to.
So the coral work was your PhD?
Hmm.
Yes. So you've had a postdoc since then, and now you're on to a second postdoc.
Yes.
Yes. Cool. That's very interesting. Cool. And how long was your postdoc looking at Martian organics?
It was 2.5 years.
2.5 years. Nice. Really get your teeth in with 2.5 years at least.
Yeah. No, it took most of that to learn an entirely new subject.
So, I think that's something people don't appreciate is, and I definitely appreciate that you have the mindset to be able to do that. And we had Dr. Matt Baum from the Open University on a few episodes ago, and he's clearly mastered the ability to take a technique and apply it to different planets and areas. And yeah, I really admire being able to just go, you know what, I'm just going to learn a whole different planet and just apply my technique to it. So yeah, that's very impressive.
To be honest, that seems to be what you have to do if you want to stay in academia at the moment with the job market.
Yeah, so you said you took a year out between the PhD and then the postdoc.
Yeah, there wasn't a voluntary year out.
Okay. Yeah, so was it mostly just applying for things, or were you
Just constantly applying for things.
Yeah. I mean, I guess perseverance is the key, isn't it? I suppose this has come up a lot when we've talked to very different people. That you've just got to sort of stick with it, I suppose. And
John, Perseverance is a rover.
Oh, that's Martian rover. Yes.
Yeah.
I mean,
It's easy to get confused between the two, though. I completely understand.
Yeah.
True.
It's a very fitting name where you're looking at academia in 2020.
But yeah, I guess on a personal note, I do find it quite difficult sometimes. I remember going through the process of applying for lots of jobs, and similarly, like it takes months, and it can be quite difficult to keep that momentum going, I think.
Yeah, I've got to say, on mine and Tom's side of things, it doesn't look very appealing. Just hearing the number of applications people do and what it's for as well. You know, it's 6 months here, and you go, oh, but you spent 6 months applying for things.
Yes, you've probably got to move to a different city for those 6 months as well.
Yeah. Oh wow, guys!
I'm feeling very positive about.
Yeah, sorry. Somebody should probably say something optimistic now.
Are there any other bits about more Martian stuff that you'd like to chat about?
Well, we did a really cool field trip to the Atacama Desert years ago.
Yeah.
That sounds good.
I've got some robots in my background. I don't know if you can hear them.
I can hear.
Yeah.
Where? What is it?
It's a robot. Don't worry about it. It's all good. It's gone now.
What have you...
It's just a van outside. I don't know.
Very good.
I was like, what have you been doing in lockdown?
Making a robot.
Engine dust and robot building. That's
exactly.
7 months well spent.
So we chatted about analog environments on Earth, and most of the time planetary geologists were in the lab or staring at images on our computer screen. Have you managed to incorporate any field work into your research?
Yes, so there's a group out in Berlin led by 2 Dirks, and they organized I think most years a field trip out to the Atacama in Chile. This is one of the driest places on Earth, the other being the Antarctic dry valleys, but they're a lot harder to get to. And so the Atacama Desert, it even looks like Mars. It's like it's all red, dry. You don't see any signs of life, except one day we saw a really lost butterfly, which was not going to last very long out there. We just spent 10 days just living in the middle of the desert. So it's like shipping everything you need in with you. There's absolutely no excess water whatsoever, so you're not washing for that period. Sleeping under the stars because there's no chance of rain, and it's basically just digging holes for a couple of weeks to try and get subsurface samples.
Okay.
And trying to do it in because there's not much organic matter there, not to the same extent as Mars, but there's still very little there, so you have to minimize contamination completely. So I mean, it's very similar to the current coronavirus situation. So you're digging with gloves and a face mask, and also not allowing the vehicles anywhere near the sampling site, because any diesel exhaust fumes are going to overwhelm the signal. And you've shipped out big containers of liquid nitrogen to in this desert environment, which is ridiculous, to get the samples straight into there to keep them frozen and minimize anything else as well.
So you're sort of effectively ground truthing what the rovers are doing then.
That was the attempt, yeah. Yeah, it's a really interesting environment to work in. You start to see the I mean, that's really hard. So like just trying to like imagine a rover having to do this while being piloted from the Earth is ridiculous.
Did you all dress up as rovers?
Sadly not.
Get in the
Not a real
mind
analog
frame.
It was hot and unpleasant enough without fancy dress.
So you dig up these samples, these subsurface samples, and then what would you do with them? Would you have to put them in sterilized packaging?
Yeah, they was all put into sterilized packaging, avoiding plastics completely.
Wow.
Trowels were sterilized between samples, and everything was just stuck into liquid nitrogen and then shipped back to the various labs that were going to deal with it.
Cool. How deep were you digging then?
So it's really quite hard to dig there. We were having to use a pneumatic drill in places.
Oh, really?
We only got down to about 2.5 meters.
Okay.
Because there's really hard. It's called a cliche layer,
right?
Which is like a really like hard packed layer of salts, which needs a pneumatic drill to get through. So
and that's just because of the lack of rain, I guess.
Yeah, it just sort of percolates down to this level when it does rain, and that's as far as it gets. It just solidifies out there, and it's those salts which are one of the reasons why we're interested in this area, because they are the same sort of oxidizing salts that cause the problems with the rover missions.
Right.
When we analyze Atacama samples in the lab using pyrolysis, the heating technique, then we can't detect organic matter in it because those samples, those salts oxidize the organic matter in the samples just as they do on Mars.
Yeah. So should Mars have a similar layer then, I guess, deep down?
I don't think so, because I think that would involve rainwater.
Right.
Causing it to percolate down.
I do wonder though, because obviously at one point there was rain on Mars, but yeah, I don't know whether, because it seems like for Atacama, that's obviously because there's very unsustained rain. Only a small amount, enough to cause it to percolate down and cause that layer. But yeah, I don't know about for Mars, would that be the case?
Yeah, I mean, well, it's not something we've seen any evidence of yet, and I would have thought that with all of the just how much sediments we have exposed, like, say in the walls of the crater and in Mount Sharp, we would have spotted something like that.
Yeah, that's a very good point. Yeah. Interesting. So while you were in the desert, did you find any meteorites as well?
There was somebody out there looking for meteorites. They had some specialist tools for that. I think they found a few.
Oh.
But I can't remember. I was quite busy with the whole digging.
Yeah, well, that's fair enough. Yeah, that's cool. So are the types of organic compounds that you find in the desert similar to what you find on Mars? Are they very comparable?
Well, in the desert, you're just finding the evidence of like cyanobacteria, because it's the main thing that's living there. You're not finding all of the evidence of the hydrothermal systems, which is the main thing that we think we're finding on Mars.
Okay. Cool. Yeah, well, that sounds really exciting. That sounds always quite nice to get in the field like that, I suppose.
Mm.
Must have had
Seems
some beautiful
Atacama-
skies.
It must be a bit of a gauntlet for fieldwork for planetary scientists, because it seems that it's Atacama, Antarctica, or nowhere.
That's it.
Go to one of
Well-
them, and
Our PhD student, Johnny, he's now graduated, he's been doing his fieldwork down in Dorset.
Oh, really? That's
Yes,
interesting.
he's been studying a stream that's very rich in iron oxides and sulfate minerals,
Right.
because we think that might be the sort of environment that's similar to sort of Noachian Mars,
Okay.
with water flow and all of these minerals around.
Hmm.
So is that the headline then? Dorset a bit like Noachian Mars.
Pretty much, yeah. That's what the press releases said.
Yeah.
Excellent. Yeah, that's really cool.
Yeah,
a bit more accessible.
a lot more accessible.
So we've got one last question for you, if that's all right. And this is our regular question that we ask all our guests. And so, if you had to do something other than planetary science for a career, what would you do?
Well, I'm not good enough, but I'd love to be a professional climber.
Cool.
That's a good answer.
Cool.
Yeah.
What I spent most of my year out doing, working at a climbing wall.
Oh wow,
that's
that must have
nice.
been fun.
It was for a bit.
Yeah.
I guess you've not been able to do much climbing then the past few months.
No,
Climbing
I don't think
walls
I
are
do that much at all.
Yeah. Are climbing walls open at the moment, or are they all open?
They are open, yeah.
Okay, right.
Okay.
That's
Do you
something else.
ever do any climbing outside?
Yes, that's the main thing.
Oh, cool.
I'm doing
cool.
when I'm not working.
Yeah, nice. I think I'm a bit too scared of heights for climbing. I don't like being on like suspended on little things, like, you know, the little footholds and stuff
Mm,
when I'm in a big high up space.
yeah, it's not for everyone.
Yeah. No, that's cool though. Where's the most exciting place you've been climbing?
We did to be honest, it's mostly just like cruddy little crags around the Peak District.
Fair enough. Well, yeah,
Yeah,
that's all right. Yeah.
Yeah.
More into trying to climb harder stuff than higher stuff.
Yeah.
Cool.
Amazing. Well, thanks so much for coming on, Sam. Best of luck with the rest of lockdown, and hopefully all of our work gets back on track.
Mm.
Cheers.
Hoping, yeah.
If to all our listeners, thank you again for listening this week. And if you'd like some more Earth and planetary science content, we have an Instagram page, we're on Twitter, Facebook, and then there's also the Earth and Solar System blog. So all the links will be in the episode description. But yes, thanks again for listening, and thanks again, Sam. Goodbye till next week.
Thanks for having me.
Bye, everyone.